Hey everyone, this is a quick look at this practice test for the second unit of Try 2. So it's all about integration, and there are lots of ways to approach the accumulation of area under a curve. In this case, we have the limit form. This is the original idea. How we find the area by making infinitely thin slices. So our slice number is going to infinity. We're adding up each slice. Know how to do this. There's good help out there in Delta Math and Khan. But 2 is our starting point. So our integral is going to start at 2. So we're looking for 2's down here. And then we're going 5 more spaces because it's all of our slices dividing by n. So our width of our slice, our dx, is 5 over n. And then we move one slice at a time, so that 5 over n represents the width of a slice. And then we're slicing it once, twice, 3 times, 4 times, all the way up to infinity. So know how this works. When you get that, you'll very quickly see that it is the integral of the ln of our x from 2 to 7. Okay, so now here we're actually finding an area under a curve using a right-hand Riemann sum with 4 equal subdivisions. So I'm looking at from -2 to 2. Each width is 1. That's kind of boring. Sometimes it's 2, sometimes it's 1/2, sometimes it's some other number in between. But you want to go to each interval and go to the right-hand side where it hits the function. And the right-hand side where it hits the function here is at when x is 0. And here's the right-hand side, and so on. So I've added up each height. Each is really times a little invisible 1. And then when you add that all up, you've got an area of 7.5 units, okay? So now this is our first indefinite integral. There's no bounds. We're trying to look for the function that when I take the derivative of it, I get this exactly. You can do these in your head with a little bit of practice. You're just going to toss in a 1/3. But formally, if we let u be equal to 3x, and we go through our u substitution, we get 1/3 the sine of 3x. The nice thing about these is you can quite quickly take the derivative of this, applying the chain rule. The derivative of the sine is the cosine, then the derivative of the inside is your 3, which when you multiply will cancel, and it'll give you that cosine of 3x. Then next page, here's another a little bit more complicated u sub. Again, we're looking for something that when we take the derivative of it, we can find a piece of it there. So the derivative of an x squared will go down to an x. We can take out the fraction to make it work. That's what all this is showing you how to do. I take 1/8 of du, and that's exactly equal to x dx, so I can get rid of this x dx this way. And it becomes much simpler, as you can see over here. And you just have to make sure you don't lose track of your 1/8 or your negative sign. Very carefully, you get this. On to the next one, where we're just interpreting the integral by an area. This could be a portion of a circle. It could be straight line. You just want to figure out what the area is under this quote-unquote curve or straight line from -3 to x. And x in this case is 1. So that's why I'm at 1 right there. Obviously, if that had been a 4, we'd go all the way out to 4. When you add up the portions of the squares or the triangles, I found it easiest to take and draw a flat line across. That's 4 by 4 is 8. And then half of a 6 rectangle and half of a 2 square rectangle gives me that math. Now into this one. This is another u sub here. If I'm letting my u be the ln of x, when I take the derivative, I get 1 over x, and that's my 1 over x down there. So again, when I make this substitution, I'm getting sort of a twofer. Out comes the x dx, and I end up with just 1/2 ln of x plus c. Originally there was no correct answer, but now I think you have a version where you would have the option of none of those, and none of these is correct, so you got to go with that. Okay, then on to the next page, where we have a fundamental theorem of calculus question. You know this because we're defining a function as an integral, and our upper bound is x squared. So if you realize how we do our integration and we are subbing in our upper bound, we sub in that x squared and we put it back in for t, and so that's x squared squared gives me x to the 4th. Sub in x squared for t and we get x squared, as you take the derivative, right, because we're looking for the derivative of g, I'll take the derivative of the outside, not messing with the inside, and then the derivative of my 2x that's going in for t. The derivative of x squared is 2x. C is your option, okay? Now this one is also a u sub, where when you take the derivative of this u, it turns into a number, and of course I can make my number 1 there just by factoring out a 1/5. This is a definite integral, so we're not coming up with a general form, we're actually finding the area under this curve when we go through things very carefully, not losing our 1/5 and doing the anti-derivation carefully. We get, oh, I shouldn't have a plus c up there, I don't need a plus c, this is a definite integral. When I do my substitution then for my lower and upper bound, I get 2 times the square root of 9 when I plug in 1, and 2 times the square root of 4 when I plug in 0, and I wind up with 2. Don't forget the 1/5, so that's your answer there, 2/5. In the home stretch here, now I've got just a very simple, I guess none of this is always simple, but it's a anti-derivation through a power rule, so there's no u sub or anything else going on. Just grind this out very carefully. It's easier because we've got zeros and ones. That always makes doing the math a little bit easier. If you go carefully, you wind up with just a couple of fractions to add, and you get your answer, okay? On to the calculator portion. So know how to put data into your calculator. If you need a refresher course, there's plenty of videos online that'll show you. Basically, once you're in stat mode, you can just go to edit. I've got list 1 and list 2, and I put in my data there. When I go to plot it, I can hit y equals, and I'll see that plot 1 is turned on right here. If it's not turned on, I can turn it on either by mousing up to it and selecting it, or going second and y equals, and then I can go right into the world of plot 1, and I can turn it on, and I can also make absolutely sure my list 1 and list 2 are correct. If I want to go down and change that, all I need to do is like second, and then if I wanted to make that L3 I would, but I want it to be L1, so I'll go back second, I'll hit the number 1, and there's L1. Once I'm done with that, to find the regression equation, I hit stat again and go to calc. Notice I'm not going to the calc above the trace, I'm going to stat and then to calc, and I want to go all the way down to the logarithmic. That's the LN, the natural logarithmic regression. And when I hit enter there, it's asking me about this regression equation, and I have to, in some calculators, tell it list 1 and list 2. On the newer ones, make sure you do that. This one, the default setting is L1 and L2. So when I hit that, I will get a plus b ln of x, and so that tells me my equation, which I have written down here as my equation. Oh yes, to backtrack a little bit, sorry I forgot this. To use trapezoidal approximation, I simply imagine I'm making, in this case, 3 trapezoids. Each trapezoid, I add the bases, that's the sides. I'm adding them there and then averaging them and multiplying by how wide it is. The width from 10 to 24 is 14. So I go very carefully multiplying each by the width. The distance from 24 to 90 is 66. Averaging 40 and 56 are my values here. So I average those, I average those, I average those, and then I multiply by the width of each of these here. So you can be kind of systematic about it and work through it. I got 6,608 meters. Back to this problem again. Here's my regression equation. When I go to graph it, I can type those into my y equals very carefully, and then I just go over, and when I've typed it in, I hit graph, and now there's my data. Oh, zoom stat, zoom 9 will fit that. If I just hit zoom and then go down to 9, or just hit the number 9, that'll fit it inside the window. When I want to find the area, you're actually not asked to find the area up to 140 seconds, but you're actually going to go out to 3 minutes, which is 180 seconds. So I need to zoom out a little bit or go to my window, and I need to get X up to, let's go to 200 seconds. and I can have my scale be every like 50 or maybe 60 seconds, or 30 seconds is a half minute. That's kind of sensible. And then I'm going to go, my Y value, I'll go up to like say 75, so I have plenty of room. And then if I just hit graph from there, that'll show me. And in the end, I want to just integrate. So you should know how to do this. You go to math. Let's see, I can do, yeah, I'll go to do it on the equation screen. I'll go second calc, and then I'm going to go down to option number 7, and my lower bound is 10, and then my upper bound is 180, and I hit enter, and I should watch it fill in all the way up to 180 seconds, and my total distance traveled is 9290, and there it is down there. So I did the integral from 1 to 140 just to check my work, and I was very close, so I'm confident that that's good. I would expect my work up here to be an underestimate because of my little picture here. The LN curve is concave down, so the corners of my trapezoid will be below that area of concavity. Okay, so that's my calculus-based explanation for all of that. All right, know how to use the calculator. If you're unable to plot it or graph it, there's not a lot I can do, so just you want to practice with that. Good luck.